Okay, let's move into chapter 10 now, chemical bonding 1. And some of this is going to be kind of review. We're just going to take some of the knowledge we already have and mesh it together with some of our quantum mechanical knowledge or our knowledge of where electrons are. All right, first thing we're going to look at is Lewis dot symbols. Lewis came up with a system of tracking valence electrons. And what he noted when you look at the periodic table, lithium 1s2, 2s1 has one valence electron. So Lewis said, okay, lithium, I'm just going to put a dot. And this dot right here represents that valence electron, the one valence electron on lithium. When we looked at beryllium, it has two valence electrons. And so what Lewis did was put one dot on this side, one dot on the other side. Note, the truth is he could put, or you can put a dot here and a dot up here, there, or a dot over here and a dot down there. It doesn't matter where the dots are. The only thing is the two dots cannot be right next to each other. This might seem a little bit weird because when we look at the Lewis structure, or excuse me, the electron configuration for beryllium, we see it's 1s2, 2s2. Shouldn't the two valence electrons be paired in the 2s orbital? Well, if we're just talking about a beryllium atom, yes, that would be the case. Those two electrons would be paired together. One would think you should draw them right next to each other. But the thing is, what Lewis was looking at is how these things are going to bond. And what he found out was if you're going to want to put these electrons on the atom in a way that's going to tell you how it's going to bond, the best way to do it is not to put two electrons together until all four sides are taken up by electrons. For example, boron has three valence electrons. 1, 2, 3 valence electrons here. Carbon has 4 valence electrons. 1, 2, 3, 4 valence electrons. Now each side has a valence electron. Nitrogen has 5 valence electrons. So now that nitrogen has one extra valence electron, we're going to have to put two together on the top. Doesn't matter where you put the two, and then 3 by themselves. Oxygen has 6 valence electrons. So it has 1, 2, 3, 4, 5, 6 valence electrons here. Note, if we look at the electron configuration of oxygen, it is 1s2, and then the valence is 2s2, 2p4. 1, 2, 3, 4, 5, 6 electrons would be put in this way if we're looking at this chart. But if we're going to note that almost corresponds to the way oxygen does look here. 2 electrons bonded here, 2 electrons are together, not bonded, 2 electrons in the same orbital here, 2 here. It kind of looks like that's what oxygen should be. But realize Lewis is just saying, hey, when we look at oxygen, we realize that it's going to react as if it's got 2 places where we have electrons missing. A pair here, a pair here. We need a pair here and a pair there to make an octet. But that's how it's going to react, which is why carbon is drawn this way, beryllium is drawn this way. When we get into what's called hybridization in chapter 11, you will see how Lewis's way of doing this makes perfect sense. All right. Note, once you get up to neon, neon has 8 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8, all are there. And if you drew it out this way, you would see that neon would have all of its electrons paired up also. All right. Ionic compounds. Remember, ionic compounds are between a metal and a nonmetal. They form our ions. We'll look at that a little bit further. Look at K2S, potassium sulfide. If we did the Lewis dot symbols, we note that potassium has 1 valence electron, so K with its dot. Sulfur has 6 valence electrons. You put in 1, 2, 3, 4, pair up 5, pair up 6. So we got 2 lone pairs, as we say, and 2 single electrons here. Note, to get its octet, to get 8 electrons, the sulfur needs 2 electrons more. Each potassium has 1 electron, so if we had 2 potassiums, each providing 1 electron, each electron would go to the sulfur. Our 2 potassiums would each be positively charged. 2 potassiums means we have a 2 plus charge. The sulfur has its octet. It has 2 more electrons than it did before. It only had 6, now it has 8, so it's the 2 minus charge. So in an ionic compound, the electron from the cation gets taken in completely by the anion to give that anion its full octet, and each atom now has charge to it. When we look at ionic compounds, there's a concept called lattice energy that really tells us how stable these compounds are, these ionic compounds. Right. It's defined as the energy associated with making an ionic compound or ionic compounds from ions in the gas phase. Note that is not how you normally make ionic compounds. You really never just take ions, put them in the gas phase, that is difficult to do, and then just have them come back down on a deposition reaction and go from gas to the solid. That's rarely done. And so this lattice energy is actually very difficult to measure. However, we can use something like the Bohr-Haber cycles, which is much like Hess's law, to get this lattice energy. Note it's delta H, not lattice. It's an enthalpy, this lattice energy. And so remember when we had Hess's law, where we took various reactions, added them up together, and then added their delta H's to get the total enthalpy of the reaction? We're going to do the same thing with a Bohr-Haber cycle to look at how we can calculate lattice energies. And it's more complicated than I like, so we're not going to worry about it too much. Let me just show you the book. I'm just more interested in what the Bohr-Haber cycle is and how we get lattice energies. We're not going to worry too much about you figuring out or doing any calculations using the Bohr-Haber cycle. Because, yeah, there it is. But here's how it goes if you were going to do the calculation. The question is sodium chloride. What is the lattice energy for sodium chloride? The energy it takes to make this ionic compound of alternating sodium and sodium ions and chloride ions. Well, here's the deal. In order to actually measure the lattice energy, you'd have to get way up here. Sodium ions in the gas phase, chloride ions in the gas phase, and then you'd have to find their energy and then compare that energy to the energy of your solid, and that would be our lattice energy. This delta H from going to the gas phase ions to the solid is our lattice energy, and that's difficult to do. So what we do is we say, all right, if we start here with solid sodium and chlorine gas in a 1 to 1/2 molar ratio, because that's where we normally start with, we can actually measure how much energy it takes to get the solid sodium into sodium gas. What is the energy of vaporization going from solid to the liquid sodium and liquid to gaseous sodium? That's not difficult to get. So we can get the energy from taking solid sodium to gaseous sodium. Now we can take the energy of taking Cl2 gas into just Cl atoms. We can find that energy. And then how much energy does it take to take that Na gas and make Na plus? Turns out if you want to take chlorine gas to chlorine minus, that a little energy gets taken away. That's an exothermic reaction. But this is measurable, this is measurable, this is measurable, this is measurable. This is just delta HF. This is just our heat of formation, so that's measurable. All these things are measurable, therefore you take these, add them all together, and you get that step, the lattice energy. It's kind of confusing. The book has the math. We're not going to do any math with lattice energies for exam purposes. The main point of lattice energy is just, okay, given a lattice energy value, can you tell me what it means? That's the main thing we're going to be interested in. Seeing a lattice energy, what does it mean? So let's look at that. All right. The first thing to remember is Coulombs Law, and we've written Coulombs Law a couple times, but here's a slightly different way of writing Coulombs Law down here. All right. The energy of attraction is going to be 1 over 4 pi E naught. Don't worry about that. That's just a constant. Energy equals a constant. Times the charge of the first thing times the charge of the second thing divided by the radius, the distance between the two atoms or the two nuclei. That's just Coulombs Law. What we're going to look at is, okay, what does that mean for our lattice energy, for how stable these ionic solids really are? And what we see is what Coulombs Law tells us. The higher the charge of the ions, the more attraction between the two. A 2 plus charge is more strongly attracted to a 1 plus charge than a 1 minus charge than a 1 plus and a 1 minus. 1 plus and 1 minus are attracted to each other, but 2 plus is twice the attraction to a 1 minus. Higher charged ions mean more attraction. The more attraction means the more exothermic the lattice energy is when those two come together. They're very strongly attracted to each other. It took energy to separate those two charged particles. When you bring them together, that energy is given off. It's an exothermic process. The energy is given off when you bring the two charged particles together. The stronger the attraction, the more energy is given off. The more stable the solid, the more negative the lattice energy is, the more stable that thing is. Also, since R is in the denominator, the smaller R is, the larger the energy is. So smaller ions have more attraction also. So that's our big take-home message with the lattice energy. It's large ions do not attract each other as much. Low-charged ions do not attract each other as much. Small, highly charged ions form very stable solids. It's another way of looking at it. All right. So here's a more typical exam type question. I could say, all right, let's look at this. Which of these things has the higher lattice energy? Which means what's the more stable solid? All right. Let's look at LiCl versus CsCl. Now, hopefully you have your periodic table handy, and you can look at this and say, okay, LiCl, note Cl is the same, and Cl is 1 minus, Li is 1 plus, Cs is 1 plus. If we look at the periodic table, we see Li is up here, Cs is way down here, which means Cs is larger than lithium. Cesium atom is larger than, or cesium ion is larger than the lithium ion, and we found out if the ion is larger, that means the radius, r, the distance between the two, is also larger, a less strong attraction. Since both lithium and cesium are +1, but cesium is larger, we know that this molecule here is going to have a smaller, a less negative lattice energy than lithium chloride. Lithium chloride with the smaller +1 is going to be more attracted. Lithium with a smaller +1 is going to be more attracted to the chloride than cesium with the large +1 due to the size. So in this example here, lithium chloride has the more negative lattice energy. We call it the larger lattice energy. Lithium chloride solid is more stable than cesium chloride solid. But what about lithium chloride versus magnesium sulfide? Ooh, that's crazy. Well, we know lithium is small, and we've got chloride there, so let's look at magnesium. Well, on the periodic table, here's lithium and here's magnesium. Well, size is interesting here. Magnesium's a little bit bigger, but note magnesium is a 2 plus charge. Magnesium is 2 plus. Okay. Which means that's going to give us twice the amount of attraction between the magnesium and a negative charge. Note that this is chloride versus sulfide. Here's chloride, here is sulfide. Note that sulfide is 2 minus, whereas chloride is 1 minus. We have a 2 plus magnesium being attracted to a 2 minus sulfur. That means this interaction due to charges is going to be 4 times as great as the interaction of lithium chloride due to charges. 1 and 1, 1 times 1 is 1. 2 times 2 is 4. So we've got 4 times the attraction due to charges of the magnesium sulfide. Now magnesium's a little bit bigger and sulfide is also a little bit bigger, but are they twice as big? If we look at the table of sizes, we see magnesium is not twice as big as lithium, sulfur is not twice as big as chloride. Therefore, with this one, we can reason that magnesium sulfide is the stronger interaction here. So magnesium sulfide would have the higher lattice energy. All right, ionic bonding, it's fine, but most people, including me, find it boring. Let's look at covalent bonding, because that's where all of the fun is. Fun meaning stuff we have to figure out, the more intense knowledge. All right, covalent bonding, recall that's sharing electrons and using Lewis dot structures. If we have a hydrogen and the oxygen and they need to share, recall hydrogen doesn't want an octet, hydrogen just wants 2 electrons around it, but oxygen wants an octet. So if you have this hydrogen with its 1 electron and this oxygen with its 6 electrons drawn this way, as Lewis dot structures are, we know that this electron and this electron can get together. Oxygen and hydrogen can share those electrons. Note, that would leave oxygen 1, 2, 3, 4, 5, 6. We can count those 2 electrons that are being shared together for oxygen. 6, 7 here. So oxygen needs another hydrogen. If we had another hydrogen on the other side, look at this. Hydrogen gives its electron to share. This hydrogen gives its electron to share here. So oxygen has its 6 electrons, but it's sharing 2 more. The nice thing about covalent bonding, we get to double count the electrons. If we look at the oxygen, we can circle all of the electrons around it. It's what we call its lone pairs, those 2 pairs of electrons that were originally on the oxygen, plus 2 bonding pairs, the shared pairs between the oxygen and the hydrogen. 2 lone pairs, 2 shared pairs make 8 total electrons around this oxygen. The hydrogen has its 1 pair that it's sharing, those 2 electrons with the oxygen, and this hydrogen also is sharing. So note, we count these 2 electrons, so hydrogen is happy because we count them for hydrogen, but we also count them for oxygen. That's the nice thing about sharing electrons, you get to double count the bonding pairs. And normally, to make things easier, we're going to say, okay, here's our oxygen. The bonding pairs we're going to draw as lines, because this gets a little complicated to look at. So we're just going to draw a line between the oxygen and the hydrogen. This line means a covalent bond. That means 2 electrons. Anytime you see a line between 2 atoms, that means 2 electrons in a covalent bond. Those 2 electrons are shared. So this would have a bonding pair here, a bonding pair here, and 2 lone pairs of electrons on that oxygen. But now, what if we have 2 oxygen atoms? What if we just want to bind an oxygen to an oxygen? Well, Lewis dot structures say here's 1 oxygen, here's the other oxygen, each with their 6 valence electrons. Note, as we mentioned before, you don't have to draw them necessarily in the electrons around oxygen just like this. You can draw, as long as you have a lone pair or a pair here, and then 2 individual electrons. Doesn't matter where you put them around that oxygen. But note, if we were to share this pair right here, then each oxygen would have 1, 2, 3, 4, 5, 6, 7 from that sharing. It wants 8. So how do we get an octet? Well, if we shared this pair and we shared these 2 electrons down here. So we're going to share these 2 electrons between the 2 oxygens and these 2 electrons between the 2 oxygens. And we're going to write that, well, if we've got a covalent bond is 2 electrons. Here we have 2 electrons here. Here we have 2 electrons here. 2 lines. We call that a double bond. And when we count the electrons, recall all electrons in a bond get double counted. So this oxygen on the right side has 1, 2, 3, 4, 5, 6, 7, 8. The oxygen on the left side, 1, 2, 3, 4, 5, 6, 7, 8, since we double count. And now each oxygen has its octet, and we have this double bond between the 2 oxygens. Let's move on to nitrogen. If we have two nitrogens, what is going to happen here? Well, Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. How are we going to get 8 valence electrons? Through sharing between two nitrogens? The way to do it is share the top pair, share the middle pair, share the bottom pair, and we have a triple bond here. Note each nitrogen has a lone pair and is triple bonded to the other nitrogen. 1, 2, 3, 4, 5, 6 electrons of the triple bond, 7, 8 give us this nitrogen's octet, and this nitrogen's the same. 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen has its octet. And going through these, making these molecules in this fashion by saying, okay, looking at the Lewis dot formulas for each element and knowing that they need octets except for hydrogen that just wants 2, how do we make molecules? Okay. These are called Lewis structures, and right now we're going through the bare bones of it. We're going to, in a future video, give you some rules that make it easier, a little bit easier for drawing these Lewis structures with larger, more complicated molecules. But let's look at something here. Using what we have done so far, I have this molecule, H3CCH3, and the structure tells me that these 3 hydrogens are bonded to this carbon. These 3 hydrogens are bonded to this carbon. Therefore, that carbon must be bonded to the next carbon over. What is the Lewis structure for this? Well, I can do this all fancy. Here's a hydrogen with its electron. Here's a hydrogen with its electron. The hydrogen with its electron. I've got my carbon with 4 electrons, 1, 2, 3, 4. I know these 3 hydrogens are bonded to this carbon, which means, okay, I need to pair these 2 electrons to give hydrogen 2 and give carbon a shared pair. These 2 electrons I can share, and these 2 electrons I can share. And if we look at the other carbon, we see the other carbon has 4 electrons. There's a Lewis dot structure for carbon. And we've got its 3 hydrogens. And we say, okay, well, I can pair up those 2 electrons. I can pair up those 2 electrons. I can pair up these 2 electrons. And note, I've got 2 electrons here on the 2 carbons. I've got to form a bond there, so I've got those 2. All right. Ooh, that looks nasty. Can we clean this up by making any bonding pair into a line? Well, sure. Here's carbon is sharing a pair of electrons with this hydrogen, sharing a pair of electrons with this one, sharing a pair of electrons with this one. The carbon and carbon are sharing a pair of electrons. And this carbon, note, has 3 hydrogens on it, each with a 2-electron bond. And when we look at this Lewis structure for this molecule, does everything have its octet? And we see, well, yeah, well, hydrogen only wants 2 electrons, so each of these hydrogens is fine. And each carbon, let's look at this carbon, how many electrons around it? 1, 2, 3, 4, 5, 6, 7, 8. It's got its octet. This carbon, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that works. Well, let's look at the next one here. We're not going to go through all of this, but we'll skip some steps. H2CCH2. Well, I know that I've seen this before. I'm going to have H2 like this. I know 1 electron comes from the hydrogen, 1 from the carbon, 1 from the hydrogen, 1 from the carbon. I know carbon has 2 more electrons on it. The next carbon has its 2 hydrogens. Note, 1 electron from this hydrogen, 1 electron from this hydrogen, 1 from the carbon, 1 from the carbon. I need 2 more electrons here. Now the question is, how do I give this carbon its octet? It has 1, 2, 3, 4, 5,